1 minute ago, California's iconic coastline just lifted 6 feet into the air. And the reason why is terrifying every scientist who's seen the data. Imagine waking up to find hundreds of miles of shoreline from San Francisco to Los Angeles suddenly perched above the waves. No earthquake, no warning, no explanation. Just land that should take millennia to move, rising in a single night while the world slept. Beaches stranded high and dry, ports crippled overnight. Marine life dying in tide pools the ocean can no longer reach. And every sensor from NASA's Jet Propulsion Laboratory to local GPS networks screaming the same impossible message. The ground moved 6 feet vertically in hours. This isn't a drill. This isn't a glitch. And scientists cannot explain what caused it. Is this the beginning of an unprecedented geological catastrophe? Or proof that everything we think we know about how the Earth works is fundamentally wrong? The answer begins with understanding what should be impossible. California's coastline sits at the razor's edge of 2 massive tectonic plates, the Pacific and the North American. For millions of years, this boundary has been locked in a slow, grinding dance. The kind of movement so gradual, you'd need instruments to detect it. Most of the time, the land creeps upward or downward at a pace measured in millimeters. 0 to 4 millimeters per year, to be exact. That's a rate so slow, it would take an entire human lifetime to notice just a few inches of change. This is the natural rhythm of the coast. The baseline confirmed by decades of meticulous records from ground-based GPS stations, satellite radar systems, and coastal tide gauges. Scientists at NASA's Jet Propulsion Laboratory have spent years perfecting instruments capable of detecting vertical land motion with extraordinary precision. Their tools can measure changes smaller than the thickness of a human fingernail. In the Santa Barbara Basin, for example, carefully calibrated sensors track uplift of just 2 or 3 millimeters per year, barely enough to register on a standard ruler. In other locations like Long Beach, human activity sometimes nudges the numbers. Oil extraction pulls fluids from deep underground, causing the surface to sink. Groundwater pumping does the same thing. Sometimes water injection pushes it back up a bit. But even these human-induced changes happen gradually, a few centimeters over the course of an entire year, never more. And here's the thing most people don't realize. The majority of California's coast isn't rising at all. It's actually sinking. As groundwater is drained and sediment beneath sprawling cities compacts under the weight of development, the land slowly subsides. When uplift does occur, it's measured, steady, and predictable. Every vertical movement along the coast gets logged, cross-checked, and validated across multiple independent monitoring networks. Satellite interferometry, ground-based GPS stations, traditional tide markers installed generations ago. Each system watches the others, each data point reinforcing the same story over and over again. Vertical land motion here is measured in millimeters per year, not feet per day, not inches per hour, millimeters per year. Marin Gavorchan, a remote sensing scientist at JPL, explained it in the simplest terms possible. In many parts of the world, especially on reclaimed ground beneath cities like San Francisco, the land is moving downward faster than sea level is rising. For geologists and geodesists, these tiny measurements represent the baseline, the expected rhythm of a living, shifting coastline. Anything faster would be unusual. Anything dramatically faster would be unthinkable, which is exactly why what happened overnight has left the entire scientific community in a state of shocked disbelief. No one in the scientific community had ever seen numbers like this. The idea that California's coast could jump several feet in a single night wasn't just unlikely. It was, by every known measure, physically impossible. To put this in perspective, the most dramatic uplift ever recorded in places like Santa Barbara topped out at 3 millimeters per year. That's roughly the thickness of a credit card, and it took 12 full months to accumulate. Even the rare documented cases of human-caused uplift, scenarios involving groundwater recharge in the Santa Barbara Basin or industrial fluid injection in Long Beach, barely managed to push the land upward by a centimeter or two over an entire year, and those were considered extreme events. The rest of the coastline, including all major population centers, typically sinks rather than rises. So when GPS stations scattered up and down the California coast began reporting sudden vertical jumps of 6 feet in the span of a single night, alarm bells didn't just ring, they shattered. These instruments are engineered to catch the most subtle shifts imaginable. They log every millimeter of movement with precision that borders on the obsessive. Their data streams are continuously cross-validated against satellite radar interferometry, coastal tide gauges, and old-fashioned surveying techniques that date back generations. All of it checked and rechecked by teams of analysts at NASA's Jet Propulsion Laboratory, the United States Geological Survey, and university research centers across the country. The probability of every single system simultaneously failing in exactly the same way is beyond astronomical. It approaches mathematical impossibility. Marin Gavorchin, that same remote sensing scientist at JPL, summed up the collective disbelief in a statement that's been circulating through the scientific community like wildfire. If these numbers are real, we're not just rewriting textbooks, we're questioning the ground we literally stand on. The accepted science is clear and unambiguous. Only a massive earthquake or a volcanic eruption could move the Earth's surface this much, this fast. But here's the problem. The seismic networks were completely silent. No tremors, no rumbles, not even the faintest blip on any seismograph anywhere along the coast. The land just rose, quietly, uniformly, everywhere at once. This left the experts facing a choice that none of them wanted to make. Either the world's most advanced geological monitoring network had catastrophically failed on a scale never before witnessed, or something was happening to the planet that no existing theory could explain. As raw data continued pouring in from stations across the region, teams scrambled into emergency mode, audit every sensor, recheck every satellite pass, comb through every line of processing code, find the glitch, find the error, find anything that would make this nightmare make sense. Engineers at the Jet Propulsion Laboratory launched their audit with a single, fundamental question. Could the data actually be trusted? The first step was retrieving the original Rhinex files from every GPS station that had reported the vertical jump. These are raw data files, unfiltered, unprocessed, time-stamped down to the millisecond. They serve as the absolute backbone of any vertical motion analysis. Each file was meticulously checked against station maintenance logs, antenna specifications, installation records, even the geological composition of the soil beneath each concrete monument that anchors the equipment. The team combed through geodetic reference frames, hunting for any evidence of a silent shift in the global coordinate system that might create the illusion of sudden ground motion. In theory, a simple misalignment in the International Terrestrial Reference Frame could make it appear as though the ground had leapt upward when nothing had actually moved. But the anomalies didn't stop there. Atmospheric modeling became the next line of defense. Engineers pored over tropospheric and ionospheric correction tables, searching for signal distortions caused by severe weather or solar activity. Even a brief lapse in atmospheric calibration during a storm can introduce several centimeters of error into GPS measurements. But the supposed uplift dwarfed any known atmospheric artifact by multiple orders of magnitude. The cross-checks extended further. INSAR radar data stacks from multiple satellites, tide gauge logs from dozens of coastal stations. If the GPS signals had been corrupted by some systematic error, the radar satellites and mechanical tide gauges should show no corresponding change. They operate on completely different principles. They can't all fail the same way at the same time. But here's what stunned everyone. The first batch of INSAR data, processed independently by a different team using different software, showed the exact same impossible step change in elevation. Engineers scribbled notes in their field books, cycling through every known failure mode. Reference frame error, multipath interference, phase unwrapping glitch. Each possible culprit was systematically tested and ruled out. As the audit deepened, moving through layer after layer of validation, the team's confidence in their own instruments began to waver. The usual suspects, the errors that cause false alarms in geophysical data, simply could not account for a 6-foot vertical leap. With every additional test, every new cross-check, the mystery only intensified. The process that was supposed to restore confidence and identify the problem instead left scientists staring at numbers that refused to make any kind of sense. Every anomaly in geophysical monitoring has a history, a catalogue of false alarms and misinterpretations. The audit team at JPL understood that the difference between identifying a real crisis and chasing a digital ghost often comes down to catching the smallest errors, the kind that slip through when everyone is desperate for answers and working under intense pressure. Multipath distortion moved to the top of the suspect list. This is what happens when GPS signals bounce off buildings, standing water, or even parked vehicles before reaching the receiver. Those reflected signals can trick the equipment into reporting that the ground is higher or lower than it actually is. But the coastal GPS stations along California weren't installed in urban canyons or near reflective surfaces. They're deliberately positioned on open bluffs, anchored in reinforced concrete, specifically designed to minimize multipath effects. Engineers pulled up the multipath diagnostic logs, searching for telltale signal spikes. The patterns came back clean. No evidence of reflected signals anywhere near strong enough to fake a 6-foot displacement. Next came the specter of phase unwrapping errors. In radar interferometry, the satellite sends down a radar wave and measures how that wave changes as it bounces back. The software processing this data has to calculate how many complete wave cycles occurred. Get that calculation wrong, and you can turn a gentle slope into what looks like a vertical cliff. It's a known problem, one that researchers are trained to watch for. The team ran phase coherence checks across hundreds of INSAR image frames, comparing each apparent jump with its immediate neighbors. If the uplift was just an algorithm making a mistake, the error signature would show up in isolated pixels or along the edges of areas with poor radar coherence, low-quality data zones. Instead, the vertical displacement stretched in a perfect, unbroken line for hundreds of miles, cutting across dense city blocks, empty farmland, and rocky coastal headlands with equal consistency. This brings us to the gold standard in geodesy: redundancy. A real geophysical signal must appear consistently across every independent measurement system. ground-based GPS, satellite radar, traditional optical leveling surveys. At each monitored site, engineers compared timestamps and raw instrument readings. Basic protocol says that if a single station glitches, the surrounding stations should remain flat. But the data showed something else entirely. The leap was everywhere, all at once. Even the tide gauges, which measure sea level height relative to the land they're attached to, reported the same sudden drop in relative water height, a mirror image of the uplift observed on shore. The statistical probability of every instrument, every methodology, every monitoring network failing in precisely the same way at exactly the same moment is impossible to calculate. It's beyond the realm of random chance. With each additional cross-check, the list of plausible explanations grew shorter and shorter. The usual technical artifacts, multipath errors, phase unwrapping mistakes, reference frame drift. None of them could account for the scale or the uniformity of the signal. The data didn't just refuse to break under scrutiny, it reinforced itself at every turn. What remained on the table was a signal that matched no known instrumentation error and no known natural geological process. The possibility that the California coastline had actually lifted 6 feet overnight, without warning and without any identifiable cause, hung in the laboratory air. Impossible to dismiss outright, equally impossible to explain. Long before satellite networks tracked every tremor in real time, California's coast already carried a well-earned reputation for instability. In 1956, a stretch of coastal bluff in an area called Portuguese Bend, located just south of Los Angeles, began to move. Residents woke up one morning to find cracks zigzagging across their lawns and the pavement in their streets. Over the next 7 months, the ground beneath their homes shifted more than 22 feet. By the time spring arrived, 140 houses had been damaged or destroyed outright. Entire neighborhoods reduced to ruins. Eyewitnesses described the experience as living on a slow-motion conveyor belt, one that never fully stopped. It would pause for a while, then lurch forward again with each new round of winter rainstorms. That ancient landslide never truly settled. Not really. Decades passed, but the ground just kept creeping, sometimes at the pace of an inch per week, sometimes faster. Then came the winters of 2022 and 2023. California was hammered by atmospheric rivers, storm systems that dumped more than twice the normal annual rainfall in a matter of months. The water didn't just saturate the surface. It soaked deep into the clay layers beneath the hills, recharging old slide plains that had been dormant for years and pushing groundwater tables to levels unseen in living memory. Monitoring sensors recorded the land moving at rates up to 30 centimeters per week. That's 10 times faster than anything in the historical record for this area. The active landslide zone ballooned from 380 acres to over 700 acres, swallowing roads, homes, and even newly developed neighborhoods as it expanded. Geotechnical engineering teams drilled exploratory boreholes and discovered something alarming: a new, deeper sliding layer, one that had remained hidden and inactive for decades, suddenly mobilized by the sheer weight of all that infiltrated water. Municipal briefings confirmed what field measurements were showing. The entire mass of land was moving, not just at the surface, but deep underground, along multiple failure planes. Each week brought fresh reports: buckled pavement, fractured water mains, utility lines stretched beyond their breaking point. In packed community meetings, longtime residents shared memories of the 1950s destruction and asked the question no one wanted to answer: Would the land ever stop moving? Or was this just the beginning of something far worse? Deep beneath the rolling hills of Portuguese Bend, the hidden machinery of the Earth operates with brutal mechanical efficiency. When relentless winter rains seep through the topsoil, they don't just saturate the upper layers. The water filters downward into ancient clay beds, softening the material and reducing its sheer strength. Once that happens, gravity takes over. Thousands of tons of earth begin sliding seaward along a slick, gently inclined failure plane. The physics are straightforward. Water lubricates the clay. Weight overwhelms friction. The hillside moves. But the story doesn't end with the landslide's slow crawl toward the ocean. At the landslide's leading edge, what engineers call the toe, a completely different mechanical process takes over. As the massive block of land grinds forward, its front edge inevitably slams into harder, more resistant bedrock formations near the coast. The advancing mass can't easily push through, so instead, it compresses. The result is a buildup of pressure so intense that the ground itself begins to buckle and bulge upward. Engineers have a technical term for this phenomenon: toe uplift. It's a physical deformation of the landscape that occurs when advancing Earth literally has nowhere else to go but up. In documented landslide cases from around the world, sensors have captured toe uplift occurring at rates ranging from several millimeters to a few centimeters per year. At Portuguese Bend specifically, while exact uplift rates at the toe remain difficult to measure with precision, the underlying mechanics are unmistakable and well understood. Compression at the toe creates surface expressions, domed ground, fresh fractures, sudden bulges that ripple across the coastal bluff like waves frozen in soil and rock. Field teams from JPL and various local geological agencies have extensively mapped these features using modern GNSS positioning systems and in SAR satellite radar. They're tracking not just the horizontal slide motion, but also the vertical deformation pulse that occurs at the front edge of the moving mass. The data collected shows clear patterns of localized uplift that match textbook models of landslide mechanics, even if the precise millimeter-scale rates at the specific toe location remain somewhat elusive due to measurement challenges. This type of ground movement doesn't require an earthquake. It doesn't need a volcanic eruption, just water infiltration, gravitational force, and the stubborn geometry of California's coastal topography. The land itself, caught between unstoppable motion and immovable bedrock, rises in defiance of its own crushing weight. It's a stark reminder that even in the complete absence of dramatic seismic activity, the forces actively reshaping California's shoreline are anything but quiet. Port officials at Los Angeles and Long Beach woke to face a crisis that no emergency response plan had ever contemplated. Container ships worth hundreds of millions of dollars lay stranded on exposed mudflats. Harbor cranes and dock workers could only stare helplessly at cargo that had no way to move. In the span of a single night, the nation's two busiest seaports had been severed from the Pacific Ocean. More than $1.4 billion in daily trade ground to an immediate halt. By noon, insurance companies were scrambling to calculate preliminary loss figures. Supply chain managers across the country realized with growing horror that fresh produce, critical electronics, automotive parts, all of it would either spoil in place or sit indefinitely with no viable path to reach American distribution centers. Harbor masters documented the chaos in real time over overwhelmed radio channels. Reports flooded in of commercial fishing vessels perched awkwardly above the new waterline, their hulls resting on sand and rock where tides had floated them just hours before. In Monterey, Port Weneme, and Oakland, the story was exactly the same. Docks left high and dry, shipping schedules torn to pieces. As word spread through maritime networks, something close to panic set in. Every major port facility along the California coast had been simultaneously crippled. On the beaches themselves, the environmental devastation became apparent even faster. Tide pools that had sheltered starfish, sea anemones, crabs, and countless other species for countless generations now baked under direct sunlight, completely unreachable by the receding ocean. Marine biologists from institutions like the Monterey Bay Aquarium rushed to organize emergency rescue operations. They put out calls for volunteers armed with buckets, wet towels, and any kind of makeshift temporary pools they could improvise. Hundreds of seabirds and marine mammals floundered in confusion where breaking surf should have been. Emergency response crews worked through the night without stopping, but the sheer scale of the disaster overwhelmed their resources almost immediately. For every animal they managed to save and relocate, dozens more died, stranded, and exposed. The shock and horror weren't limited to scientists and emergency responders. Local residents posted videos across social media. Mass strandings, desperate, chaotic rescue attempts. The haunting, unnatural silence left behind as the living edge of the coastline was abruptly pushed out of reach. The human cost, measured in economic disruption, was staggering. The ecological cost, measured in lives lost and ecosystems destroyed, was incalculable, and both continued mounting with every passing hour. GeoStride, a well-funded Silicon Valley satellite analytics firm, released their own independent analysis within hours of the coastal UPLIFT event. Their proprietary algorithms, processing data from commercial satellite constellations, showed the same 6-foot vertical displacement. But their measurements came with even sharper spatial precision than the government monitoring networks had achieved. Almost immediately, the United States Geological Survey issued a rare public challenge to those findings. The USGS released a carefully worded statement warning that satellite-only measurements can be distorted by atmospheric interference, particularly during certain weather conditions, and by subtle biases in processing software. GeoStride responded aggressively, accusing the USGS of institutional resistance to new technology, of clinging to outdated ground-based sensors while ignoring clear evidence visible from orbit. News organizations began publishing leaked internal emails that revealed scientists on both sides scrambling to defend not just their data, but their professional reputations. On social media platforms, rival experts traded increasingly sharp criticisms over calibration protocols and the reliability of open-source processing code. Behind the scenes, a flood of Freedom of Information Act requests targeted both agencies. Reporters demanded access to raw data files, internal communications, and any hint of classified information that might explain the impossible event. Conspiracy theories gained traction almost instantly. Had there been a secret military experiment gone catastrophically wrong? Underground nuclear testing, covert drilling operations? The Department of Defense issued a terse denial, but the rumors refused to die. Insurance companies, already overwhelmed by the port closures and stranded cargo vessels, watched their exposure skyrocket. Claims spiked by billions of dollars in a single day. Existing policies that covered damage from earthquakes or tsunamis were suddenly legally worthless. This disaster had no official classification, no precedent, no actuarial tables. The debate over what had caused the uplift rapidly spiraled into something much larger and more troubling, a fundamental contest over who controls the narrative of reality itself. If the data was accurate, then foundational rules of geology had been violated. If the data was flawed, then the world's most sophisticated and expensive monitoring infrastructure had failed at its only critical job. With every new press release, every technical rebuttal, every leaked memo, the gap between the two camps only widened. No one could definitively say what would happen next. No one could predict if the coastline would continue rising, stabilize, or somehow return to its previous elevation. The only absolute certainty was this: the foundations of geological science and the literal ground beneath millions of California residents had never felt less secure. In the past 24 hours, GPS networks and INSAR satellite radar systems have confirmed vertical land movement measuring up to 6 feet along more than 400 miles of California's coastline, an event that no historical record and no peer-reviewed scientific study has ever documented at this scale or speed. Multiple independent investigation teams have ruled out sensor malfunction through exhaustive cross-validated field audits and original data file reviews. Yet the observed uplift pattern does not match the signature of any known earthquake mechanism, volcanic activity, or landslide precedent. While the Portuguese Bend case demonstrates that rapid localized uplift can occur through landslide toe compression mechanics, nothing in the published scientific literature accounts for the geographic scope or the remarkable uniformity now being witnessed from San Francisco to Los Angeles. Official reports from the United States Geological Survey and private sector firms remain contradictory and incomplete. Several key data sets are still under internal review. Others have been classified. As major ports sit idle and marine rescue teams continue working around the clock to save stranded wildlife, California faces an unprecedented crisis with no clear scientific explanation. For now, the cause of this coastal rise remains unproven, and the question of what comes next is a matter of urgent, deeply unsettled inquiry.